All right, so in class last time we did a little lecture on section 16.4, how to do triple integrals. Let me just remind you slightly of how that's going to work. If you integrate something where okay, so I should probably say this is really a triple integral over some region in three-dimensional space. We usually call the regions R when we're in 2D and something else when we're in 3D, just to try to distinguish. But it's still just a volume of space, some region that we're integrating over. And there'll be some function, let's call it phi of x, y, and z in here. And the integral is done with respect to volume. We say dv. So that is, one of the ways you can interpret a thing like this, phi here might be a density. Might give you the density of some substance as a function of where you are in the thing. And density times a volume is a mass. So when you integrate, you add up a whole bunch of differential masses and you get mass. Right, there's a whole section on doing mass calculations coming up. So this is never the way you actually calculate, though. When you go to calculate, you have to have limits in iterated integrals, and that's going to look something like this. I'm going to add in some extra decorations just to make it clear what's going on. This is x values, x from a to b. These functions are actually y values. So y is going from f of x to g of x. And the innermost integral, z with functions, well, I don't know. How about r of x and y? And z equals s of x and y. So that is, you can have functions of two variables on the innermost integral, one variable on the middle integral, and it's got to be constants on the outer integral, or else you're not going to end up getting a number out of this. You have your phi of x, y, and z in here. Oops. Need a comma there. And dv becomes, well, in this particular one, it becomes dz times dy times dx. That is, you just mentioned those in the correct order, that you can think of this as the z integral, and then the y integral, and finally the x integral. So we looked at that. Now, today we want to concentrate on sort of what is the meaning of that. And it's, well, that is reasonably simple. It's a little chunk of the volume of space that you're talking about, whose height is dz, whose width is dx, and whose depth, try to make it look 3D now, the depth there is dy. Think of those as little, like, at least, well, really we should think of them as something that's approaching 0, but I always like to draw them as if they weren't quite that tiny. Anyway, there's more than one way to do dv. And it comes down to that there's more than one way to do coordinates. This whole picture that I've shown you is, well, this whole setup that I've shown you has to do with using the Cartesian coordinate system, the system where x goes horizontally, z goes vertically, and y goes into the board. Those are particularly nice coordinates to use because of perpendicularity. Each axis is perpendicular to the other one, so they kind of don't interfere with each other. You get a nice simple formula for the differential volume. But in certain circumstances, it's not the coordinate system you want to use. Let me give you an example. Suppose I was trying to figure out the total mass of the sun. There's a density function for the sun, which we actually know, just from theory. We know that the solar matter gets denser as you go in, because it's under pressure from more and more mass lying above it. Gravity contracts the whole thing. So we have a solid understanding of how the density works as a function of where you are in the sun, and it's spherically symmetric. Almost. The sun actually rotates rather rapidly, so it's not quite as round of a ball as you might imagine. In fact, it's more oblate than I think than any of the planets are, but it's still close enough to a sphere that you can hardly tell the difference. Anyway, well, without instruments, you can't tell the difference. So this function of density, which is, symmetrical in a spherical way, is very easy. But if I try to calculate what density is as a function of x, y, and z, ooh. And also the surface of the sun would be like z equals square root of 1 minus x squared minus y squared, and then the negative of that underneath. The boundaries, even in the plane, would become circle parts with square roots and stuff, and the integral would be horribly messy. But the sun is a ball, or it's a sphere, so a coordinate system that takes advantage of that natural shape, or a coordinate system that makes sense in that shape, is actually the thing to go for. So with that in mind, there are two new coordinate systems that we're going to look at in this next section, 16.5. And one is pretty straightforward, pretty easy, and the other is a good bit tougher. The one that's tougher is the one we'd use for the sun, spherical coordinates. But let's start with the easier one, cylindrical coordinates, and then move on to the tougher guy later. What makes cylindrical coordinates sort of easier to understand is that you've essentially, you've done the hard part by understanding polar coordinates. So the way cylindrical coordinates work, I'm trying to draw a z-axis and imagine a xy plane down below. What you do is you do polar coordinates in the plane. So you have different angles coming out from the center, and then you'll have different radial amounts out from the center. You've seen this kind of thing before. In fact, when we turned on Desmos and looked at it, I wish I hadn't drawn the boundaries of the plane before I started putting in the traces for how polar coordinates look. Anyway, so you locate yourself in the plane in polar coordinates, and then you just, suppose here's theta, and here's r. There's that much angle, that much r. I'm at a point in the plane. Now I just go up from there. And the coordinates of that point, if the length of the height that I go above the plane is z, that would be r, theta, and z. So it's really, it's just basically polar coordinates plus a height. Cylindrical coordinates aren't too hard to understand. The big question then, not a huge question, but a question is, what's dV? What is dV in this kind of system? So we should think about a little volume, a little chunk of the volume in space that's got a tiny amount of angle and a tiny amount of radius and a tiny amount of z, of height, difference between its surfaces. So that is, I'm going to try to draw a fairly big one out here. In the radial direction, we may have something like that. In the theta direction, in the angular direction, we want to make it look, do those look like they're converging? Here's here's a differential amount of theta, right? And then dz just gives it some height. So this thing that I've drawn so far, except for that I'm trying to draw it in perspective, that's a polar rectangle. If I give it some height, that's just taking that rectangle and either going up or down. I'm going to go down because I think it makes the picture look better. This surface in here is curved, right? The back surface is curved as well, but this one's flat, except it's got it's rebowed. Anyway, I hope you get the idea. This is a polar rectangle times a dz height change. So what's its volume? Well, you know what the area of that polar rectangle is. Remember that was, in fact, one way we could say this is it's the differential area times a dz that you get the differential volume out of. But we also already know what the differential area is. In polar coordinates, it's r d theta. So here we go, r dr d theta, and then dz. Not too bad. It's basically the product of differential radius, differential angle, differential z, but there's an extra factor, that r that comes in. But that came about from polar coordinates. We'd already dealt with that r before. When we try to do things spherically, this is going to be tougher. So let's try to, well, before I pass on to that, I do want to mention that a lot of times you'll see this sort of cylindrical coordinate system in machines like robots, and some 3D printers have this kind of scheme too. You'll have an arm that can lengthen and shorten, and then it can be moved up and moved down, but it can also be rotated around. So there are ways to mechanically make a thing that naturally has cylindrical coordinates is the kind of right system to use. Spherical coordinates, well, actually, the one place where I think people are pretty used to spherical coordinates is the surface of the Earth. So, the only problem with the surface of the Earth is you pretty much are stuck on the surface, so your R isn't changing. We just joined those two up. It's supposed to be spherical coordinates. Yeah, so how does spherical coordinates work? Let me draw the Earth's surface for you. The North Pole sticks out about there. There are lines that go this way down towards the South Pole, which is just under the curve of the Earth now for us. And these are called lines of longitude. The longitude lines happen because at the center of the Earth, you can imagine sweeping out a slight angle. So, for instance, the one that passes right through the Greenwich Observatory in England is called 0 degrees. And, you know, what I've shown here is probably about 10 degrees east. So those things, they look like more or less vertical lines. Of course, they're curved because they're on the surface of the sphere, but they're just on the surface. In fact, you can think of them as half planes. There's an entire plane's worth of stuff that's at 0 degrees. If we could get off the surface of the Earth, maybe in a spacecraft or airplane or something, we could be along not just this line, but on that plane somewhere. We could be at 0 degrees longitude, but you know, at a different radius. All right, so what's the other type of lines you see on the surface of the Earth? They're the ones that go more or less horizontal, in this orientation. Like that one looks like the equator, which is 0 degrees latitude. And then there's other lines that go up like this. There eventually comes a point where we get to see that these are actually circles. You know, they're, yeah, all right, so the lines of latitude come from thinking about, you know, well, I guess calling the equator 0 makes sense. There's this plane through the surface of the Earth, and angles of latitude are measured from the center of the Earth up to different amounts. And you know, once you get up to like an 80-degree angle, it's pointing way up like that, and that's when you spin it around. That's what draws that Arctic Circle. All right. So I think people know those, latitude and longitude. The longitude is the same in the usual coordinate system as people do it, or at least as mathematicians do it. Longitude is the same, but latitude is not. What we usually use instead of latitude, which is measured both up and down from the plane that goes through the center of the thing, we use what's called colatitude, which is the angle strictly down from the North Pole. All right, so what are we going to have to locate a thing in spherical coordinates? We're going to have theta, which is like a longitude. We're going to have phi, which is a co-latitude. And then we're going to have distance out from the center of the sphere. And I know we always call that r, but because spherical is different enough, people usually use rho for this. This is radius. Oops. So an angle, let me try to mime this for you. You have an angle that sort of goes from some point marked on the sphere all the way around the sphere. That's theta. You'll have an angle that goes from straight up down to your point, and then finally you'll have a radius to figure out how far the point is. I was trying to think about different ways to sort of illustrate this to you. Let me give it a try. All right, so let's try to illustrate the spherical coordinates. But what I want you to imagine is I'm trying to locate a point in space. And we'll do that relative to my head being the center of the system. Actually, I can't put this tape measure in the middle of my head, so I'm going to like put it on against my ear, say, right? So here's the scheme. I'm going to first rotate my head until I'm facing the general direction of the point I want to find. Then I'm going to spin this tape measure down until it's got the right angle to run into the thing. And then finally, I'm going to extend the thing until, you know, it runs into the point I'm after. That's the idea. Spin and sort of rotate in the plane, then come down from due north to the angle that you want to, you know, that will take you in the direction of the point you're trying to locate, and then give the actual radius out to that point. It's a pretty natural coordinate system, but differential volume in spherical is tough. So let's try to sketch for you a piece of differential volume. If you're a fan of like honeydew melon or cantaloupes or things like that, that's a good image to put in your mind. So what I want to do is imagine a thing that has a particular change in the radius. That's actually not so bad. If I think about sweeping out a part of volume where I just change the radius a little bit and leave everything else to float wherever it is, I get essentially a hollow sphere. So that's why I think of a melon is the right idea, except there's seeds in the middle with a real melon. But you know, you scoop those out anyway. So let me try to draw for you a wedge taken out of a honeydew melon. Fairly thin. There would be a part of it that we can't see, another edge of it right back there. So I've turned it so the outer peel is somewhat towards us. All right? So this thickness here to here, that's the rho. That's a change in radius. So the center of the sphere this thing came out of was right there. And how wide of a wedge it is, that's a little bit hard to draw. I'm going to try to draw it in perspective here. That amount of angle, that's d theta. If I want to get a differential volume now, I've also got to throw in a small change in phi. Now phi is an angle that comes from the North Pole down to a particular location, and then a small change in it would be something like that. So that would be a d phi. So what do you get if you take a slice of honeydew melon like this and then you slice it once more? You could actually do this, right? Slice a whole bunch of chunks of melon up like that. How big is this piece that we've got? What's it sort of look like? For the purposes of drawing it now, I'm going to spin it around a little bit away from us. Oops. that had to be in the radial direction. It could be worse. It could be better too. Anyway, this leg right here, that's d rho. This way, into the board, that corresponds to d theta, but it's not just d theta. You see, well, it depends where you are along this slice, how much width you've got to the thing. If I did a little, the same kind of d phi rather, down here, about the same size d phi, yeah, more or less, but this thing is much thinner than this nice chunky one in the middle. In fact, the fattest one happens right in here. So it turns out that this dimension that I'd like to know, that depends that depends on how far we are from the center, because I could have the same d phi and d theta, but be in here towards the center, and it would, it would mean I was cutting my slice out of a smaller hunk of mallet. It means that the little chunk that I'm getting here would be smaller. So this piece is really kind of complicated. It's rho times sine phi times d theta. That is, d theta gets affected by scaling by rho, but also by where we are in the slice, whether phi is near 0 or phi is near 180. When phi is 0 or 180, you get basically, it zeroes it out. You get ridiculously thin slices there. When phi is at 90 degrees, or pi over 2, that's when you're at your fattest. So it sort of makes sense that the sine of phi is the right thing to use. Yeah. Okay, so that's this way and this way. What's the other direction? This way. Now what is that? That is, well, it's proportional to d phi. But again, if you were farther in or closer in or farther out, that would change how much that length was, right? So this is actually rho times d phi. That is, it depends on rho. That length does not depend on phi or theta. It just scales if you go farther away from the origin. Now, and the other problem with this, of course, is these things are not exactly linear dimensions. This one is a curved one, that's a curved one. That's one of the beauties of passing to the limit. Once we get these things sliced up fine enough so that you're close to the limit as d rho, d theta, and d phi are going to 0, it becomes a perfect little cubelet. Well, it approaches being a perfect little cubelet. So, differential volume in spherical coordinates is this: rho squared sine phi d rho, d theta, d phi. I get a rho from each of these two, and I get a sine phi from that one, and then I get the three differential ones. Now, and those things could be mentioned in plenty of other orders, depending on how, what was convenient for doing the integrals. Yeah. Almost always, I would say, when you go to the trouble of going to spherical coordinates, your limits are going to be constants, because you move to spherical coordinates particularly because it was convenient to do so, and that usually means constant limits. That's what makes it easier. So don't get too excited about order of integration. You'll always be able to mix that around if you're dealing with constant limits, but don't forget that you have these extra factors, rho squared and sine phi, in order to get the differential volume to really be the right thing. If you leave those out in a computation, you end up finding out, discovering the sun weighs like a third as much as it's supposed to, things like that are bad. Okay, oh, transformations. Sorry, there's one last thing I want to do before we leave this. How do you go from one system to the other? So yeah, I want to do the transformations between coordinate systems. There's three of them now, and so there's potentially three different sort of transformations we should do. Now let's try them. So the first one is going to be between rectangular coordinates and cylindrical coordinates. And again, this is made easier by the fact that we've just talked about polar coordinates and you've seen them before. So for instance, if you know the cylindrical coordinates, r and theta and z, well then x is going to be r cos theta. And y is going to be r sine theta. And z is going to be z. Right? Now what if we have x and y and z and we want to get, that is, I was saying we're in cylindrical, so we know r, theta, and z, and then we want to get x, y, and z. We want to get to that system. What if instead we're in this system and we want to get to that system? Well, I think it's clear the z equals z part will stay the same. But what do we do with x and y in order to find r and theta? Well, the sum of x squared plus y squared will give you r squared. If you take the square root of that, you've got r. That's just the Pythagorean theorem in one version, right? How do we figure out the theta? Because that's the only thing missing. We've got r and z, we need theta. The easiest thing to do is just to say it's the arctan of y over x. That doesn't quite do it for us, but it comes close. What we really need is a way to go from, well, actually, what we really need is what they do in a lot of programming languages. They have a function called atan2. And atan2 takes two arguments, an x coordinate and a y coordinate, and it figures out the angle to that point. The issue is that y over x, well, for instance, if y and x were both negative, you'll have a positive number in there, so you'll be taking the inverse tan of maybe 40 degrees or something, some positive angle. But if x and y are both negative, it actually means you're back in quadrant 4, 1, 2, 3, the one where everything's negative. And that means that angle is 180 degrees more than what you think it is. So, if you actually tell it what x and y are separately, it can take it into account the sine of these two guys as well as what the angle is that corresponds to their ratio. Anyway, this is close enough, right? You use inverse tangent to find the angle. If x and y are not positive numbers, then adjust the angle so that you get it into the right quadrant. And r is the square root of x squared plus y squared. So, okay, not horrible. What about if we try to go spherical? Add spherical to the list. Well, I want to at least partly go from spherical to cylindrical. So if you're in spherical, the idea is you should imagine, you've got your origin, you've got a line that really tells you where the theta equals 0 is. And this is the z-axis, I suppose we should call it. But you're locating a point by two angles and then a distance out. The two angles are one sort of around the pole and the other down from the top of the pole. So if you let me draw that so that the around the pole looks more elliptical because it should be. This is a circle that's actually lying in the xy plane. Okay, so if we are at some angle theta around from the center, and then we come down along some angle phi from the North Pole, we land at a spot that's sort of that lies above the plane somewhere. But I guess that's the question to ask. If you know what the radius is, so if this length here is our rho, make that look like a rho, not a p, sorry, and we know what the angle is, how far is the what I would call the projected radius in the xy plane? Do you see that I've got a point located three-dimensionally because of spherical coordinates, the angle theta, the angle phi, and a distance rho, but that lies above a point in the plane. If we dropped it onto the point in the plane, where would it land? Let's just pull that whole picture out. It kind of doesn't matter what theta is. We'd have the same triangle, just oriented different ways. So I want to pull it out and square it up its view for us. There's a right angle here. The angle phi is right here between the North Pole and that thing. This is the point that's up at the tip of our radius. So the hypotenuse of this triangle is rho. And what I'm after, this length, is what we're going to call r. Now let's see. Phi is really here. That means that angle is also phi. And that makes this guy the complement of it. But let's just leave it up there. We'll look at that as being the angle. How do you get r in terms of phi and rho? It's rho times a trig function, and phi and phi and r are across from one another, right? This is the side opposite of phi. So maybe a good way to do it would be to recall to you the SOHCAHTOA business. The sine is opposite over hypotenuse. That's the SOH in SOHCAHTOA. So what we've got is that the sine of phi is equal to r over rho. And we can solve that for r. R is rho sine phi. So that distance right there is rho sine phi. That lets me basically, almost basically get the cylindrical form. So I'm going to have rho and theta and phi in spherical. In cylindrical, I'll have r. Well, let's write them out first. We'll have r and theta and z. And we've sort of got, well, we've got 2 out of the 3 of these. The thing is, theta is actually got the same letter because it's the same number. Right? It's the angle measured around from the x-axis in the plane to find the point we're after. So theta, whether you think about it as locating that point, or theta is, if you think about it locating that point, are the same. R, we just figured out, is rho times sine of phi. So we have r equals rho sine phi. Theta equals theta. And what are we going to do with z? Well, on my little picture here, z is this length. And on that triangle over there, when I brought this thing around so that we can see it square on, it's this length. So how do you get this z in terms of rho and the angle? Z is the side adjacent to the angle now. So z is rho times the cosine of phi. I'm drawing that wrong. It should be phi. I was about to make a theta. All right, so that is, if we know our coordinates in spherical, we can convert them into cylindrical. And we already know how to turn cylindrical into rectangular, so that's good. I think the only thing left is to see if we can go from cylindrical to spherical. So that's the question I'm asking. If we're in cylindrical coordinates, meaning we know r, theta, and z, can we figure out what our coordinates are in the spherical form with rho, theta, and phi? And let me just be very clear. Given those guys, find these guys. And one thing that's going to help us is the picture of the triangle that I had out there a minute ago that was drawn so that, or turned so that it was oriented straight onto us, the 90-degree angle here. It had z on that side, r on this side, and it has rho on that side. And that's a right triangle, so you know it's going to tell us what rho is, doesn't it? Rho squared is z squared plus r squared, or that is, rho is square root of z squared plus r squared. Not too bad. Theta is also really easy. Actually, theta is even easier because theta is theta. Well, what else do we need? We need the angle phi, which if you'll recall was up at this location in this triangle. We need phi. The tangent of phi is r over z, opposite over adjacent. Take the inverse tangent. Let's see, z could be both positive and negative. I'm just thinking about that issue I had with whether we need the a tan 2 or not. I think this is okay because basically r can only be positive. We normally think of it as positive. That's a lot. You can think about negative r's, but it's the same thing as if you just added 180 degrees to theta. So normally we try to imagine r being positive. All right, well that wasn't as bad as I was thinking it might be. We just knocked it out. Though there is one last stage, which is to convert from whichever one we have back to rectangular. So really, let me just try to picture this for you. Rectangular, cylindrical, spherical. We have done this way in both directions, and we have done this way in both directions. I feel a little strange about leaving out these things, but you could certainly get from spherical to rectangular by converting to cylindrical first and go back. Yeah, well, I'm going to leave it like that, and maybe in the worksheet we'll explore a little bit about how to make the direct connection between rectangular and spherical. All right, that's it for today.